This is a video for AQA Discrete Mathematics. This is Graphs and Networks section 1.1, where we're introducing the idea of graph theory. Well, graph theory is a relatively new area of mathematics and developed separately from, but is very much related to another area of mathematics called topology. So these two develop separately, and therefore you'll find that we've got different words which describe the same ideas. And you just have to get used to this when you're dealing with the discrete topic of graphs. So when we're talking about a graph in discrete mathematics, it's not the sort of thing that you have in your GCSE where you've got a set of axes and you're drawing lines. But what we do have is a graph is simply a set of points which are then joined together by lines. Now these can represent all sorts of things. They don't have to be necessarily geographically accurate, and what's important is that the things that they're representing, we are showing the connections between those points by using the lines to show the connections. So many different sort of ideas that might come about. Here's just a few. So the idea maybe relationships, where we're showing if one person is related to another, or boyfriend girlfriend, for example, might be another way idea of relationships. Route maps underground is a classic example. Utility networks, cables, gas, telephones, etc. So lots of examples, and I'm sure you can think of some of your own. So here's one of those classic examples that you'll all be familiar with, and you may not realize, but the actual position of the stations, which is what the points are representing, is not very geographical. In terms of, if you put that onto a London geographical map, those stations would not be in those positions. However, what is important is the connections, so that every point connected by a line, that is literally a line on the underground network. So we have some terminology that you need to get used to. So we talk about those points. Actually, the correct term for them is to say that the points are called nodes or vertices, and the lines are called edges or arcs. So they've got this idea of two different words describing the same thing. The degree of a vertex is how many edges come into the vertex. So in the diagram above, we can see that the vertex at the top here has got 3 edges coming in, so we could talk about that vertex as having order 3. A connected graph, it's possible to go from any vertex to any other vertex on the graph itself. So here's 2 examples. You can see that on the left hand side we have a connected graph, but on the right hand side there's a break there, so this is a graph which is not connected. Well, I'd like you to just pause the video for a little while and just try this example for yourself. So if you pause it now and then come back when you've had a thought. Well, let's see what happens when we try to build this up. So if we put in a vertex and then an arc, you can see that at the other end there must necessarily be another vertex. Now if you think about that, then the total order that we've got there is 1 plus 1. So here we've got 1 and order 1, and here we've got order 1 as well, so we've got a total of 2. And we can do that. Let's instead make this a 3 node, so we could put a loop in here. So now we've got 1 plus 3 giving us 4. And if you think about that a little bit more, you'll realize that the total order must be an even number, because each time we draw a arc, it adds 2 to the total order of the graph, 1 at each end. So the total order is some even number. It must be equal to 2 times something. Now, you're beginning to realize why you've perhaps had difficulty doing this one, because if you look at the total order of this, we've got 1 plus 1 plus 2 plus 3 plus 4 plus 4, and of course that's going to be an odd number. I think it's actually equal to 15, and so it's impossible to do the task that we've set you there. It's an important lesson. There is a little theorem called the Handshakelemma, which says that the total order of the vertices in a graph must be an even number. Well, changing the question around a little bit, we can ask the question then, how many edges are there if we've got vertices of a particular order? Now here you see we've got a total order of 12, so that the total order is equal to 12, and therefore the number of edges must be equal to 12 divided by 2, which is 6. So this graph will have 6 edges. And let's see if we can actually draw these. We've got the nodes 1, 1, 2, 2, 2 and 4. Let's see what we can do. Well, we could create a one node, obviously, by just simply putting a node with a line coming out, and then perhaps we might do the same there. There we are. So there we have our 2 1 nodes and a 2 node. Well, there's nothing to say that this graph needs to be connected, so there's 2 more 2 nodes, and now a 4 node we can get in that fashion. So there we have 6 nodes. One of them is a 4 node here. We've then got 3 2 nodes and 2 1 nodes. So there's an example where the graph is not connected. We could draw another one, this time trying to make it connected. So here I'm going to first of all start off by creating a 4 node. Then I want to turn the nodes at the end here, 2 of them, into 2 nodes by joining them together. Then I've got one more line. If you look at the number of lines we've got, the number of arcs rather, then we've at the moment got 5. So one more to add in, and I can create my graph there. So there's an example of the graph which is connected. Many more examples where that will work. So where we have the 6 nodes with those orders, I'm sure you can find some for yourself. Well, we used loops in that last example. So a loop is an edge that starts and finishes at the same vertex. So an example of a loop in this diagram here. And then a simple graph is one where there are no loops and multiple edges between vertices. So we don't have this type of situation or this. Those are not allowed in a simple graph. Now by the complement of a graph, so what we call G prime, it's made up of the same vertices, but then we have the vertices that are not connected in G are connected in G prime. So if we look at the diagram on the left, we can say, well, which vertices are not connected directly? Those are the two there, and so that produces G prime. A complete graph is one where every vertex is connected to every other vertex by an edge. It's also a simple, so there are no loops in there, so we can see that there we've got the complete graph. Each is a direct connection to every other one. About the number of arcs, well, the number of nodes, n being equal to 4, and each will be of order 3, because it's got to be, each node has got to be connected to every one, and so if there are 4 nodes, each of those must be of order 3. Therefore, we've got a total order of 4 multiplied by 3, so that the number of edges must be that divided by 2. 4 multiplied by 3 divided by 2 is equal to 6. What about Kn then? Well, the same argument says that the number of nodes is n. The order of each of those must be n minus 1. So that gives us a total order of n times n minus 1, so that the number of edges must be that divided by 2 for Kn. And finally, what happens if we add together a graph and its complement? Well, here's a graph that we had in an earlier question. Now if we add in the complement, there it is, and you can see what we've created there. So if we take a graph and we add its complement onto that graph, then we have created a complete graph. Well, continuing with our definitions then, a digraph is one in which one of the edges has some direction associated with it. So the diagram at the top there is not a digraph, but I could add in an arrow perhaps on one or more of these lines, and that produces then what we call a digraph or a directed graph. And there's another example of a directed graph. Notice that not all of the edges need to have an arrow on them, and if they don't, they are two-directional. A bipartite graph is where we have two sets of nodes, and the edges go from nodes on from one set to nodes on the other. So here's an example of a bipartite graph. We can talk about a complete bipartite graph where every node in one set is joined to every node in the other set. So we need to add some edges in on here. So just to do that, the first node at the top there needs to be also added to the top two on the right hand side. There's an edge missing for the next one, and then going down, nearly there now, and so just to complete it, you can see it's quite a complex graph. And we can think about how many edges are there. Well, we've got 4 nodes on the left hand side and 3 on the right hand side, so in total we must have 4 multiplied by 3 edges. Sometimes we use a table or a matrix to look at the what's called the incidence or adjacency of the nodes, and all this does is count how many edges, how many arcs are going into a node from any other node. So if we look at this diagram, the table, the top row is looking at those that are going from A, and so from A to A there are 0, from A to B there are 2, and then A is not joined to any of C, D or E directly. So it's looking at the direct ones. From B to A there are 2, and then B is joined to D and C by a single arc, but it's not joined to E. And we can continue with that. You might like to just try it yourselves. It comes down C being C to A 0, C to B 1, C to C 0, and then C to each of D and E 1s. From D we can get to B and C, so this one goes 0, 1, 1, and then 0, 0. Notice because that's a directed arc, then we can't go from D to E. And finally 0, 0, 1, 1, 2. So there we have our incidence matrix for this. One or two things that might be worth pointing out about this: what's called the leading diagonal down here is going to show a degree of symmetry if it's not directed, but you can see where we've got the directed part of the graph, then this is no longer symmetric, so we haven't got symmetry here, and that's where the directed part is. But otherwise the 2 there is reflected by the 2 in the mirror line of the leading diagonal of the matrix. The other thing to notice is that on the leading diagonals they're going to be zeros, or if it's or a loop, so that these are the number of lines which go from a point to back to itself. So the 2 at the bottom here was indicating that there is a loop from E back to E. 2 because you can go in both directions. If there was an arrow on the loop, then that would be 1. A planar graph is one which can be drawn so that no edges cross each other. Now these are drawn with crossing points, as you can see in the diagram there, but if I move the point, you can see then that it's now a planar graph. So let's just go back to that, do that again. So the point in the middle moves to the outside, and similarly with the diagram on the right, we can move the point at the top, this one here, to the outside, and it produces that as a planar graph. So those are both planar graphs. You might like to think about going back to complete graphs. Which of the complete graphs are planar graphs? Is it possible to do K3 as a planar graph, for example? There's a formula for planar graphs, which is Euler's formula, which also can be related to solids. But for planar graphs, we have F represents the number of regions that there are on the graph. Now you have to count your regions. If you look at the left-hand graph here, 1, 2, 3, but there's a 1 on the outside, so there's the outer region 4. So we have here F is equal to 4. Vertices, V for vertex, you can see here we've got vertices equal to 5, and the edges in this particular example is equal to 7. So there we can see that we have that 4 plus 5, so F plus V, 4 plus 5 minus E minus 7 is indeed equal to 2. And in all cases that will be the same. Now, on the right hand side we've added an extra edge, so you can see this here, we've added an extra vertex, and we've also added in 2 edges, and that's created an extra region. So f has gone up by 1, so f has increased by 1 when the vertex has increased by 1 and the edges has increased by 2. So you can see there that we've actually got still going to have a value of 2. So we've now got 5 plus 6 and minus 9, again giving us 2. A subdivision of graph is made when we place an extra node along a connection between 2 existing nodes. So, for example, putting in an extra node at this point, that is called a subdivision. A tree is a connected graph, so every vertex is joined to every other vertex, but there are no cycles, no loops, and no way of going round in a circle, as it were. So that's a tree, and literally it looks like branches coming out from each of the nodes. Now a graph, at the bottom you can see an example of graph. We can create a spanning tree from that. Now a spanning tree is a tree which connects each of the nodes in the graph. So the graph at the left there is not a tree, it's got a cycle in it, but we can produce a spanning tree from it, and there's one example. There are others in that graph which, or subgraphs, which produce spanning trees. Here's a question about a tree. Then how many arcs are there in a tree with 10 nodes? Well, we can think about building it up, can't we? Each time we put in a node, we've got to connect it together, but we can't put any loops in. So you can see there's a tree with 3 nodes, and it has 2 arcs, and each time we add another node in, it's going to add an arc. So we can see therefore that if we've got 10 nodes, then there must be edges equal to 9. Now if we think about Euler's formula, here we have the faces. Well, there's only one face in a tree because there's no enclosed region, so there's just the outside region, as it were. So f must be equal to 1 for all trees. So if we have vertices equal to 10, we can say that f plus v minus e is equal to 2. So using Euler's formula, we can prove then we've got 1 here plus 10 minus e is equal to 2, and therefore by that way we've got e is equal to 9. Well, putting some of these recent ideas together, then we can ask this sort of question: what's the minimum number of edges that G could have if it's a simple graph? Well, you'll gather that what we're doing, that the minimum number of edges means that it must be a tree. So it will be a tree, and therefore the edges will be equal to 7. What's the maximum it can have if it's a simple connected graph? This must be K8. It's a complete graph of 8 nodes. So therefore the number of edges will be 8 multiplied by 7 divided by 2, 28. Right, well finally now some definitions about the graphs, which seem very similar to each other, but they are subtly different. So a path, first of all. A path is a sequence of edges such that the end of a vertex on one edge is the start of the next. So, for example, a path could go from A to B to C to E to D. And no vertex is visited more than once. It is possible for the first and the last one may be the same, and if that's the case, we've got a cycle, so it's a closed path. So for example, a closed path might be B, E, C, and then back to B. So a path and a cycle are connected. A cycle is simply a closed path. And then one which again looks quite similar is the idea of a trail. But in a trail we have something where the edges are not repeated. We can go back to vertices, but we have no repeated edge. So for example, we could go from A to B to C to E to B, and then back to A using the other loop. And there you'll see that we've repeated the vertex in B, but the edges have not been repeated. So the path, we would have no vertex visited more than once, but a trail, that is allowed. Now it's been a very long video going through all these definitions. You'll get used to the definitions as we go through more and more of the videos and more examples, but I do suggest that you take some time to perhaps go through quite slowly there and make a list of these definitions, because you do need to be familiar with them. In the next video we'll be looking at some ideas which use graphs for modelling.